Hi, welcome to another day with more of this linear function story problems. So I like what I have written up here at the top. Although it can be challenging, it is critically important that students who exit Algebra 1 have a good ability to deal with linear relationships. In this lesson, we get more practice modeling linear phenomena. So let's go ahead and start with our first example. We have a warehouse is keeping track of its inventory of cardboard boxes. At the beginning of the month, they had a supply of 1,275 boxes left. They use boxes at a rate of 75 per day. So they tell you at the beginning of the month, this is and how many boxes they have, and they use boxes at a rate of 75 per day. So hopefully you see right off the bat, oh, okay, they're talking about an initial value and a rate of change. So if I have to create an equation, I'll probably be using y equals mx plus b. Let's get to part A. It says, how many boxes are left after 10 days? Show the calculation that leads to your answer. So for this one, we can start with, if we have 1,275 boxes and we're using boxes at a rate of 75 per day, that means we're taking away 75 per day, and it's going to be after 10 days. Okay, and then we can just go ahead and solve this. Okay, 75 times 10 is 750, and we get a total of 525 boxes. Okay, so it says, which of the following linear equation correctly models the number of boxes left, n, after d days? Okay, so using this connection of x and y, if I want, I can even label what x equals, what y equals. So let's do that real quick. They do talk about days, and then they talk about boxes left, n. So x is usually your independent variable, and it deals with time, so x will be your days. And so y is your boxes. Another clue is those are the two variables that they talk about in our story problem. Okay, they talk about x's, or I'm sorry, days and boxes. So which equation would work? So from part A, we realize, well, my rate of change is negative. And if I look through, I only have one that has a negative 75. And so just to double check everything else, n is boxes, and so is y. D is days, so is x, so it does match my slope-intercept form. So we can go ahead and circle 3. All right, let's go ahead on to C. So for C, it says, if the warehouse needs to order more boxes when their supply reaches 150, how many days can they wait? So let's go ahead and use this equation that we got from number 3. So we'll go ahead and use n equals 1,275 minus 75d. This question is asking how many days, okay? And they have boxes of 150. So a substitution, we'll put 150 in for n, and then we'll solve for d days. Okay, so a little bit of algebra. Subtract 1,275 from both sides. And we get negative 1,125 still equal to negative 75d. Divide both sides by 75, negative 75, and d is equal to, works out to be 15 days. Okay. Now my next one, part D, if after 5 days they start using boxes at a rate of 90 per day, how many days will it be before they run out of boxes? So this is a multi-step problem. If after 5 days they use boxes at a rate of 90 per day, how many days will it be before they run out of boxes? So what we're going to do is, our first step is to figure out, how many boxes they have after 5 days. So after 5 days, or that first 5 days, they're using the equation that we had started with, so 75. So as our rate of change. So what I'm going to do is I'm going to take that 1275 minus 75 and then multiply it by 5, because again, for the first 5 days, they're using the rate of change of 75. So when I do the math and the calculations, we get 900 boxes after 5 days. The next thing we're going to do is they increase your rate of change. So there's two equations that you can do for this one. We have a new initial value of 900. Okay, my new rate of change is 90. D, and we would set this equal to 0 because our goal is to have no boxes left when they run out of boxes, so that's 0. So we can do something like this. We can solve for D. And you know what? Let's just work with this equation that we have right here, and then later on I can show you a different one that would also work. So we have negative 90D is equal to negative 900. Divide both sides by negative 90, and D is 10 days. Okay? But I'm going to run out of room, so I apologize. I'm going to put this right here. For the first, we can't forget about the first 5 days. And then we came up with an increase of our rate of change, so plus 10, and that is 15 total days when they would run out of their boxes. Okay, so again, definitely a multi-step equation on this one. I told you there could be another equation. It could be a little bit more simple. So what you could have done is 900 is equal to 90D. Just showing you variations, okay? But since we have been working with slope-intercept form, that equation works just fine. Okay, let's go on to problem number 2. Problem number 2 says we want to feel very comfortable with quickly and accurately determining linear models. Keep in mind that the two most important aspects of any linear model are its rate of change and its starting value. Okay, and we just kind of talked about that with part 1. Number 2 says the cost C in dollars of running a particular factory that produces widgets can be modeled using the linear function. So instead of f of x, so remember this could always be f of x, and remember f of x equals y. So if y equals f of x, f of x equals c of w equals 1.25w plus 2175. This is just showing you your cost in dollars per widget. So a little bit more on that. How do you interpret the fact that C of 100 equals 2300? So remember how C or Y is the cost of running a factory. So we'll go ahead and start by the cost of running a factory when it produces 100 widgets is $2,300 per day. Okay, so they're talking about this as per day. So working some more with that function notation, we can't forget. Then part B, give a physical interpretation for the two parameters of this equation. Okay, so we have 1.25 and 2175. These are coming from our equation. So what we're going to be doing is we're going to write what these values mean in words when it pertains to this equation. So we'll go ahead and start with 1 and 25 hundredths. This represents the cost of producing one widget. Okay. Next, 2,175. Okay. This is a fixed cost. Okay. So let's start with that, and then we'll talk a little bit more about what a fixed cost means. Okay. It costs $2,175 to run the factory even if no widgets are produced. So there's lots of things that can run into that. Insurance, taxes, your electrical bills, other kind of utility bills, those sorts of things. Okay, so let's go ahead and write that down, that it will cost $2,175 to run the factory even if no widgets, squeeze that in here, even if no widgets are produced. Okay? Alrighty, so we are done with the front. Let's flip it over on the back. Exercise 3, there's a lot going on with exercise 3, and I think it'll be best if we do this next time I see you in class. So let's go down to exercise number 4. Number 4 is a bit of a review with rate of change, using some more story problems with rate of change. So number 4 talks about waters draining out of a bathtub such that the volume still left, G gallons, is shown as a function of the number of minutes, M, it has been draining. We're going to calculate the average rate of change, G, over the interval 0 is less than or equal to T, which is less than or equal to 2, and we're going to make sure we include proper units. Okay? So what we're going to start with is we are going to remember that average rate of change, okay, it is the change of y over the change of x. Remember, when we are finding change, we're going to subtract, okay? And so what they're giving us, if I want to put this into words, we have x, y, okay? We have time, that's our t, so this is given to us as x. I can do 2 minus 0. And then I have to find the corresponding y value. So when x is 2, y is 28. When x is 0, y is 62. Okay, and then I'm just going to simplify. So I get negative 34 over 2. To keep simplifying, I have negative 17. Oops. And then let's go ahead and put our units on here. So this is negative 17 gallons per minute. Okay, so we know gallons is on top because our change of y is on top. So negative 17 gallons per minute. I ran into B a little bit on that one. Okay, so part B says calculate the average rate of change of G over the interval of T is less than or equal to time, which is less than or equal to 4. Include proper units. So this is the same idea as A, finding the average rate of change. Okay, and so we'll go ahead and use that same formula as we did for part A, where it is the change of y over the change of x. So we're finding the difference between from 4 to 2. So when x is 4, y is 12. Or if I want to say when our time is 2, our gallons is 28. Okay, and then let's just simplify. I get negative 16 over 2. And to keep simplifying, it is negative 8 gallons per minute. And now for part C. What can we say that the relationship between M and G is not linear? I'm sorry, not what. Why can we say that they are not linear? So it's giving us a clue that it is not linear. So let's double check what we have going in our table. Right here, that all increases by 2. So that part is a constant rate of change. But let's find the difference between each of these. So 62 minus 28, we get a decrease of 34. 28 minus 12 is a decrease of 16, and 12 minus 5 is a decrease of 7. So that is one way to see that it is nonlinear. Another way is to compare the two slopes. Do you see how the two slopes are also different? So our rates of change are also different. So let's kind of write this down, what it means to be linear. So in a linear relationship, the average rate of change, it remains constant. And when I talk about constant, I'm talking about it being the same. So, in this case, my two rates of change are different. Okay, so again, we use two different ways to tell that we do not have a linear relationship. We found the average rate of change of each, and the slopes are different, and then we also looked at our values in the table, and we saw in the table that we saw a different rate of change there. Okay, hey, that's it for these notes. I'll see you guys next time in class. Over and out.